Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. SPHEREx, mapping the universe in infrared, one spectrum at a time. The SPHEREx spectrophotometer for the history of the universe, epoch of reionization, and ICE's Explorer mission is an ambitious NASA project designed to conduct an all-sky spectral survey in the near-infrared. This small astrophysics satellite aims to answer fundamental questions about the origins of the universe, the evolution of galaxies, and the role of water and organic molecules in the formation of planetary systems. By capturing detailed infrared data, SPHEREx will provide a unique glimpse into both the distant past and the complex processes shaping planetary systems today. The mission is set to launch no earlier than February 27, 2025, riding aboard a SpaceX Falcon 9 rocket from Vandenberg Space Force Base in California. Infrared astronomy has long been a crucial tool for exploring the universe beyond what visible light allows. Many celestial objects, including young stars, dusty galaxies, and the earliest structures in the universe, are best observed in infrared wavelengths due to their ability to penetrate cosmic dust and reveal otherwise hidden features. SPHEREx will expand upon the legacy of previous infrared missions like Spitzer, WISE, and IRAS, but will take a different approach by scanning the entire sky multiple times in over 100 distinct infrared colors. This will create a detailed spectral map of the cosmos, providing data that will be invaluable for both cosmology and planetary science. One of the mission's core scientific goals is to investigate the large-scale structure of the universe and its connection to inflation, the rapid expansion that occurred a fraction of a second after the Big Bang. While inflation is a key component of modern cosmological models, direct observational evidence remains elusive. By measuring how galaxies are distributed across vast cosmic distances and analyzing subtle patterns in their clustering, SPHEREx will test inflationary models with unprecedented precision. The mission will look for imprints of quantum fluctuations that stretched across the universe during inflation, leaving behind faint signatures in the distribution of matter. These observations could provide direct insights into the physics of the very early universe, potentially answering questions about the fundamental nature of spacetime itself. Beyond its contributions to cosmology, SPHEREx will also serve as a powerful tool for galactic and extragalactic studies. By mapping the entire sky in near-infrared light, it will create a vast catalog of stars, galaxies, and active galactic nuclei. This will allow astronomers to study the evolution of galaxies over cosmic time, particularly how they formed and assembled into the large-scale structures we see today. Since the universe is expanding, light from distant galaxies is stretched into longer wavelengths, a phenomenon known as redshift. By analyzing this effect in detail across millions of galaxies, SPHEREx will create a three-dimensional map of the cosmos, revealing how structures evolved over billions of years. The mission's third major goal is to investigate the distribution of water and organic molecules in the Milky Way and nearby planetary systems. Water ice plays a crucial role in the formation of planets and the delivery of life-essential compounds. By detecting water and other volatiles in the interstellar medium, SPHEREx will provide critical insights into the early stages of planet formation and the potential for habitable environments beyond Earth. The mission will specifically target regions where stars and planets are actively forming, analyzing how water and organic molecules accumulate in protoplanetary disks. These observations will complement data from other missions like the James Webb Space Telescope, which focuses on individual systems in high detail, while SPHEREx will provide a broad survey of these fundamental ingredients across the galaxy. SPHEREx's ability to scan the entire sky every 6 months will also make it a valuable resource for identifying transient and variable phenomena. Infrared observations are particularly useful for detecting objects like brown dwarfs, rogue planets, and distant supernovae. Additionally, the mission will support the study of near-Earth objects, NEOs, by identifying asteroids and comets with unusual compositions. By observing their spectral fingerprints, scientists can learn more about the building blocks of the early solar system and how these bodies have evolved over time. The spacecraft itself is designed to be compact and efficient, carrying a telescope with a 20 cm aperture and 2 infrared cameras covering wavelengths from 0.75 to 5 microns. These instruments will allow it to perform low-resolution spectroscopy across a vast range of celestial targets. The mission's design prioritizes reliability and cost-effectiveness, leveraging existing technologies to maximize scientific return. Unlike larger observatories that require extensive cooling systems, SPHEREx will operate in Earth orbit without cryogenic coolants, relying instead on passive cooling techniques. This makes it a relatively low-cost mission compared to flagship observatories, but still capable of producing transformative scientific results. As the launch date approaches, engineers and scientists are finalizing the spacecraft's construction and calibration, ensuring that it will be ready for its ambitious mission. Once operational, SPHEREx will provide one of the most comprehensive spectral maps of the universe ever created, enabling discoveries across multiple fields of astronomy. The data it collects will not only address its primary science goals, but will also serve as a rich resource for future research, supporting new studies on everything from stellar evolution to the search for biosignatures in planetary systems. Once SPHEREx begins operations, its data will revolutionize multiple fields of astrophysics, offering a comprehensive spectral map of the entire sky that will serve as a foundation for future discoveries. One of the most significant contributions will be its ability to test models of cosmic inflation with an unprecedented level of detail. The early universe underwent a period of rapid expansion, and while inflation is widely accepted as the best explanation for the large-scale structure of the cosmos, direct observational evidence remains limited. SPHEREx will analyze the distribution of galaxies across cosmic time, searching for the subtle imprints left by inflation in the clustering of matter. By measuring the variation in infrared light from millions of galaxies, the mission will help distinguish between different inflationary theories, potentially providing the first clear evidence of quantum fluctuations that shaped the universe in its earliest moments. Another groundbreaking aspect of SPHEREx is its capability to trace the cosmic history of water and organic molecules within the Milky Way and nearby galaxies. While planets and planetary systems form from vast clouds of gas and dust, the exact mechanisms that govern the distribution of water in these regions remain poorly understood. SPHEREx will conduct an extensive survey of interstellar ices, identifying the locations and concentrations of water, carbon-based molecules, and other volatiles crucial for planet formation. This data will help scientists understand how these essential ingredients for life accumulate in protoplanetary disks and how they may be delivered to developing planets. By comparing regions with different star-forming conditions, SPHEREx will also shed light on how the availability of water and organic material varies across the galaxy, providing crucial insights into the likelihood of habitable environments beyond our solar system. The mission's ability to systematically map the sky every 6 months will make it an invaluable tool for studying transient and variable astronomical phenomena. Many celestial objects, including supernovae, quasars, and distant gamma-ray bursts change in brightness over time. While traditional surveys focus on either deep observations of small regions or wide-field imaging without spectral detail, SPHEREx will offer a unique combination of both approaches. By capturing low-resolution infrared spectra of the entire sky, it will identify objects with unusual or changing light signatures, helping astronomers pinpoint new supernovae, track active galactic nuclei, and discover brown dwarfs and rogue planets. These transient events could provide new insights into the physics of extreme astrophysical processes, such as black hole accretion, neutron star collisions, and the life cycles of massive stars. One of the most practical applications of SPHEREx's data will be its role in supporting future large-scale observatories. Missions like the James Webb Space Telescope, JWST, the Vera C. Rubin Observatory, and the Nancy Grace Roman Space Telescope are designed to conduct deep, targeted studies of specific astronomical objects. However, these observatories rely on survey data to determine the most promising targets for detailed follow-up. SPHEREx will serve as a crucial precursor mission, identifying interesting galaxies, exoplanetary systems, and stellar objects that merit further investigation. By providing spectral classifications for an enormous number of celestial sources, it will help optimize the use of larger, more specialized telescopes, ensuring that they focus on the most scientifically valuable targets. Beyond its planned objectives, SPHEREx is expected to generate a wealth of serendipitous discoveries. Whenever a telescope surveys the sky in a new way, it often uncovers unexpected phenomena that reshape our understanding of the universe. The infrared spectrum is particularly rich with hidden structures, such as interstellar dust clouds, faint dwarf galaxies, and previously unknown cosmic filaments. It is possible that SPHEREx will detect entirely new classes of astronomical objects or reveal unexpected relationships between known structures. Additionally, its comprehensive sky mapping will be invaluable for refining our models of stellar evolution, galactic dynamics, and even the structure of the solar system itself. The mission's impact extends beyond pure astrophysics. The all-sky spectral maps produced by SPHEREx will be freely available to the global scientific community, enabling research in fields ranging from cosmology to planetary science. The vast dataset will also support the study of exoplanets by improving our understanding of the environments where planets form. By identifying molecular signatures in different star-forming regions, SPHEREx could help refine theories about planetary atmospheres and their potential to support life. This will be particularly useful for interpreting data from future missions dedicated to exoplanet characterization, such as the Roman Space Telescope and upcoming ground-based observatories. As the launch date approaches, anticipation for SPHEREx continues to grow. Engineers are finalizing the spacecraft's construction and testing, ensuring that it can withstand the harsh conditions of space. The telescope's design, optimized for efficiency and longevity, will allow it to operate for at least 2 years in a sun-synchronous polar orbit, ensuring full sky coverage with minimal interference from Earth's atmosphere. Once in space, SPHEREx will begin its systematic mapping of the cosmos, gradually assembling a detailed infrared portrait of the entire sky. The knowledge gained from SPHEREx will shape the next generation of astronomical research, answering fundamental questions about the origins of the universe while opening new avenues for exploration. Whether it uncovers evidence for inflation, reveals new details about galaxy formation, or helps identify the building blocks of life in distant planetary systems, the mission is poised to make lasting contributions to our understanding of the cosmos. Its ability to bridge the gap between large-scale cosmology and planetary science underscores its importance as a uniquely versatile observatory. As the data begins to flow back to Earth, astronomers around the world will have a powerful new tool to decode the mysteries of the universe, marking a new era in our quest to understand our cosmic origins.